Section 8.4, Angular Variables and Tangential Variables. So up to this point, we've been considering angular velocities, where you can imagine a line of ice skaters, for instance, and if they're all traveling together in a line, then each of these ice skaters is going to sweep through an equal amount of angles in the same amount of time. So they'd all have the same angular velocity. But that doesn't mean it's the same for every ice skater there, right? In order to stay in the line, the ones that are on the far outside have to be traveling with a linear velocity that's much higher than the ones in the middle. This is known as the tangential velocity. So it's tangent to the circular path, right? It's that straight line motion. And what you'll see is that as you move to greater and greater distances from the pivot point, the larger the tangential velocity will be. One of the ways to illustrate this is with an ice skating maneuver known as crack the whip, where you get a bunch of ice skaters to skate together in a line. And I found someone's video of this from a while back, so we'll see if it plays well here. But if not, the link is there as well for you to give a shot.
Is it icy?
Yeah, so you can tell they're on ice.
Come here, Flipper. Come here, Ice.
And there the skaters go,
icy?
they're all holding hands.
It's icy.
No one on the left. Someone said 3 and stopped. And they're on the far right.
Ow. That was a clunk.
Right? We could try backing this up a little.
Icy.
See if we can watch that again.
It's icy.
There they go. And whoosh. In the end, gets going faster and can't hold on
That
anymore,
was a clunk.
nor stand upright. So,
Ouch.
tangential velocity is a real thing, right? That the person on the inside, the pivot, was still technically turning through the same angle in the same time, but didn't have to go very far. Versus on the outside, there's a whole lot more distance to travel in that time. So how do we describe that in terms of math and physics? Well, our tangential velocity is going to follow our standard definition of distance over time. So the distance is going to be the arc length, the total distance traveled, divided by the time it takes to travel that. But the arc length, we've already seen another equation for, right? Remember, arc length is the radius times the angular displacement, theta. So we can plug that in here and then regroup the theta divided by the time. Pull the r outside. If we have r times theta divided by time we've seen before too. Angular displacement over time is just our angular velocity. This finally gives us an equation for our tangential velocity or tangential speed, if you're just working with the magnitude, where you can plug in the radius times the angular velocity or angular speed, and you will get the tangential velocity. A key note here is that that angular velocity must be in the SI units of radians per second. Otherwise, it doesn't work out. So make sure that you're in radians per second, then you'll multiply by the radius, which will be something in meters, and then your units will come out to meters per second. Radians sometimes seems to disappear as a unit. It's kind of rad like that. This is our tangential velocity. We could imagine, what if the tangential velocity is increasing, right? What if it starts at one value and then starts to get larger and larger? Well, if we have a change in our tangential velocity, that's just going to be an acceleration. So the tangential acceleration is the change in tangential velocity, vt minus vt0. We can plug in our tangential velocity as r times the angular velocity minus r times the initial angular velocity. Factor out that r, we can pull it out in front, and then we notice we have the change in angular velocity divided by time, which is just our angular acceleration. We've seen that before too. So our tangential acceleration is just the radius times the angular acceleration. Notice the similarity in form here. The tangential variables are just r, the radius, times the angular version of the variables. So the radius tells you how large the tangential quantity will be. As you move further and further out, you get a larger tangential speed and a larger tangential acceleration as well. Let's try this out with an example. So a helicopter blade. The helicopter blade has an angular speed of 6.5 revolutions per second and an angular acceleration of 1.3 revs per second squared. For point 1 on the blade, find the magnitude of A, the tangential speed, and B, the tangential acceleration. Right, so we just got the equations for tangential speed and acceleration. And they rely on angular speed and angular acceleration. So that part is good news. We have to check our units though. Are our units SI units at this point? Not quite, right? We have these revs, which is just short for revolutions. That's just one complete turn. So the revolution, we've seen how to convert that before. Using 1 revolution is 2 pi radians. So we'll do that. And then we can plug and chug away. So let's take a look at that. We can convert that angular velocity, that's 6.5 revolutions per second. If we multiply by 2 pi radians per 1 revolution, we now have our angular velocity in 40.8 radians per second. That's now the right form that we can plug it into the equation for our tangential velocity or tangential speed, where we'll just need to multiply by the radius, which at point 1 is a distance of 3.0 meters. That comes out to a tangential speed of 122 meters per second. That is pretty fast, right? What about the acceleration? Well, for the acceleration, we'll follow the same process. So we're going to, again, convert that acceleration that was given to us in revolutions per second squared into radians per second squared. Revolutions is still talking about angular quantity, so that part's good. It's just not our SI unit yet. So we find that the angular acceleration is 8.17 radians per second squared. If we want to make that the tangential acceleration, we just need to multiply by the radius, 3.0 meters, which is 24.5 meters per second squared. Thus, we've solved for the tangential speed and the tangential acceleration at point 1. How would our answer compare if we instead calculated them at point 2, the very tip of the rotor blade? Well, notice point 2 is 6.7 meters out. So we'd expect that our tangential speed and our tangential acceleration would be twice as big, over twice as big to be more precise. How would the angular velocity and the angular acceleration compare? Those would be exactly the same, because the angular variables just depend on the angle that's swept out, that angular displacement, divided by the time. They don't care about that radial distance r. This introduces the way we can go from those angular variables and get them into our tangential variables. Nice introduction to that idea.